Emission spectroscopy is a method of measuring light-matter interactions. An emission spectrum is the plot of emission intensity versus wavelength. Wavelength is the distance between two peaks on a wave. Emission intensity is a proportion of the number of photons emitted at a wavelength. For each peak on an emission spectrum, the lambda max is the wavelength for which the emission intensity has the greatest value. For an electron to emit energy, it must absorb a photon first. The wavelength the photon absorbed depends on the amount of energy required to excite the electron. The energy required to excite an electron is quantized, which means each electron requires an exact amount of energy to be excited and increases energy level. If the electron remain at the higher energy level is energetically unfavorable, so the electron relaxes to a lower energy level, releasing energy in the process. This energy is released in the form of light. The amount of energy released is inversely proportional to the wavelength of the photon released.
The energy levels of electrons are different in differing molecules because the atomic composition of the molecules is different. These different energy levels determine the wavelengths of photons emitted by a substance. Whichever wavelength of photon emitted has the highest intensity is referred to as lambda max. An analogy to this would be box jumps.
A low-energy photon will excite an electron to a slightly higher energy level, just as less energy would be needed to jump to a shorter, lower box. The photon released will have a large wavelength and low energy. A high-energy photon will excite an electron to a much higher energy level, just as jumping to a higher box would require more energy. In this case, the photon released will have a low wavelength and high energy.
To see how atomic composition determines energy levels, we can look at oxygen and fluorine on the periodic table. We see that both atoms' electrons exist in two energy levels. Fluorine has more protons than oxygen, so fluorine's nucleus has a stronger attractive pull on its electrons, which means fluorine's electrons have a lower average potential energy than oxygen's. So fluorine would require more energy to excite an electron from the first energy level to the second. Lambda max refers to the wavelength of the photon with the greatest emission intensity. The red line is the one-to-one mixture of green and red dye. This mixture appears as a neon orange color. On the red line, we've determined the lambda max to be about 616 nanometers. 616 nanometers falls slightly inside the range of orange light, but very close to red. If lambda max determined the observed color, then the color would have been a very red-orange, but the mixture appeared as a neon orange to us. Therefore, observed color does not determine lambda max because if it did, lambda max would have been closer to the yellow wavelength at about 590 to 600 nanometers.